Doesn't mean be tall. All right. So, any case, first step, when I'm looking at electrolytic cells, I understand that one has to be driven, meaning one is not spontaneous, of course. And every time I'm going to give you electrolytic cell scenario, although, to be perfectly honest, I got these questions I built from 2 separate AP questions. So I've made them a heck of a lot harder than you have to have them for AP. This would be next to a battery already. They wouldn't make you identify the battery with it. Guess what I am, because I want you to think deeply. So this is a lot harder. These questions, parts of them are from past AP Part 2 questions. So they're a lot easier, but I'm asking you to think deep and understand, have this with you. So first step, okay, I'm looking at, and you will see this skill on your test, is that there's electrolytic and there's a galvanic or voltaic. Galvanic, voltaic are the spontaneous. They're the batteries. Luigi Galvani, Alessandro Volta. I gave you the story because I want you to know that those words represent a spontaneous redox reaction. And notice they have to be separated. Good at oxidizing, good at reducing, and you're going to have some type of salt bridge involved. So this screams cell B to be my voltaic cell. Okay, so I'm just for fun, I'm going to write that, okay, voltaic cell there, just to remind myself. Probably don't need to, but what gives it away is the salt bridge. Separation of what? Places where oxidation and reduction occur. Notice in my cell A here, I don't have that scenario. Oh, Christmas in July. I don't have that scenario because this is going to make it happen. I don't have to separate. I don't need a salt bridge because it's not going to work by itself. We're going to force it to happen. We're going to force something to happen here and here. Okay, so this, of course, is my electrolytic. Okay. And I just write that there for my viewing pleasures. Okay, so now, in order to do the list of things that I have written here, list all the anodes, cathode, with charges, flow of charge, and provide arrows to show how the salt bridge ions are moved. And these are a bunch of different ones. I gave you 2 checks for the anodes and cathodes. The reason for that is you could do one cell right, but then mess up the other. Okay? If you mess up who the anode and cathode is of the battery, then obviously your anode and cathode in your electrolytic cell will be different. So if you messed up who the anode and cathode is here, but you put them correctly what they would be based on that incorrect, you would get a check. Okay? No double jeopardy in my quizzes, so make sure. So every quiz is kind of graded differently based upon what you did. So if you did the anode and cathode correctly, identified what they were based upon the hints in the question, but you set up the anode and cathode here incorrectly, again, 1 out of 2 checks, all right? And it can be both ways. Any case, the first step is I've got to look at my voltaic cell and who is the anode and cathode. Now, typically I could take my half reactions and or my net potential table, okay, and look at 2 metals and see who is better at oxidizing, who has the greatest negative standard reduction value. I couldn't do it in this case. Always going to give you a brand new scenario. You looked up thallium, okay, in your standard reduction table, it wasn't listed. It wasn't listed for a reason, because the AP or myself didn't want you to go that route. But normally you could. Here you couldn't. So we had to go to the clue. And the clue was right here. It's observed in cell B that when the silver metal, notice I can't do anything until I figure out my anode and cathode in the battery. Why? Because the battery drives the electrolytic. Electrolytic does nothing, has no charge anywhere until I define what the battery's doing. Okay, battery is spontaneous. So, this is my hint. Okay, it's observed in cell B that when silver metal, okay, is placed, so let's draw it. Piece of silver metal, Ag, argentum as Latin would say, is placed in thallium fluoride. Okay, and I gave it to you. TLF. Okay, not TL2F, TLF. You should be able, even though you haven't had any experience with thallium, you should know there's 1 thallium to 1 fluorine. Fluorine, if you look at your reference tables, likes to become -1, like all of the halogens. So this breaks apart to F -1 and thallium +1. Some of you guys are using +2. you look at the formula and see what ions you have. It's a one-to-one relationship. So it's got nothing to do with the fluorine. It's got to do with the what? Okay? So what we're saying here is that silver metal is placed in thallium fluoride. No reaction occurs. That means Tl plus 1 cannot do what? Cannot force silver to what? Oxidize. Thallium fluoride is not good enough. And in terms of attracting electrons, to pull electrons, it is not a strong enough oxidizer or oxidizing agent. So there's nothing that occurs here. Now, why is that a hint? Well, going back to here, okay, so this doesn't occur. So thallium plus is terrible in reacting here. So what does that tell me? What's that?
It's going to be good reacting.
Right. If I'm terrible at becoming an ion that gains electrons, so this is so good that you did this. So thallium is terrible at doing what? Gaining electron to become Tl, 0. What could you say the voltage would be if you could see it? Negative some number. And if I'm terrible, here comes our big understanding. If I am terrible in this pathway, what's it telling you? I'm really good in the other pathway. So that screams to you that this guy loves to oxidize. Okay? And that is why that is my anode. Okay? If it did pull electrons, then this would be positive. And therefore, thallium in the reverse would not be what? Would not be good at oxidizing. And there you can make a case for silver being the anode. So that was the hint. And if you got messed up there in that little curveball, I get that. Okay? But you've got to be ready for that. And I did something this summer where we dipped copper in tin solution and tin in copper solution, and one worked and one didn't. And understand this. If this was the guy that's going to reduce, if this is the cathode, if you said this was the cathode, then you're saying that this is good at doing what? Pulling electrons. Okay? Or you said that the fluoride is good at pulling electrons, but that's in the salt bridge, right? Look at it. It's in both places. All right? Any case. So right away I know this is my anode. And if that tripped you up, I feel bad a little bit, but that's just how it goes sometimes, and it's only a quiz. So let's make this the anode. Which we know is what charge? Negative. Negative. And I like to put the charges in here because this is the place where thallium is going to give up electrons. Thallium is going to give up electrons here, so that's where it's negative. Electrons are coming from that. Now we're going to use the anode and connect it to the cathode. Now the question is, I gave you a hint where, and this is what the AP did. They made a separate battery to say, okay, can you understand where the cathode is? So I'm telling you this reaction, we're producing protons, producing BrO3. So party people, look at my half reactions given. These are not in your reference tables. They're giving you these. Where am I producing BrO3? Oh, and protons. Right there, party people, and people that want to go to the party. Right, I'm producing them, but in my half reaction, they're reactants. So what must this half reaction be doing? Booming this way. And if we're reversing it this way, aren't I producing electrons? And if I'm producing electrons, isn't that oxidation? So what they were telling you by that hint, that this must be the what? The anode of the electrolytic cell. Oh, thanks. And therefore that this must be the what? Now, how do we make this the cathode? Well, the cathode is the place where red cat occurs, reduction. You need electrons to force onto something. Where does it get its electrons? The source of electrons is the anode of the battery. So party people, we're going to connect the anode to this cathode. And we know electrons always flow from anode to cathode. So if anyone messed up their anode to cathode, as long as whatever you put anode to cathode, full credit. Okay, so that's why. So no matter what you did here, As long as I saw your anode to cathode, full credit. But if you drew electrons from cathode to anode, that makes no sense. Who produces electrons? The one that oxidizes, anox. Okay? And by the way, if this is negative, this makes this what? Negative. Cool beans if beans are chilled. Now, this must be the cathode. Back to the other blue, I have no idea. So this is the cathode of the battery. It must be positive. And why by convention? Because we know to close the circuit, electrons have to flow back there. So we make it positive by convention. No one discovered these charges. We use them to make sense of that. There's no little microscope. Oh, there's the little negative charges. So we want the anode to attract to the cathode. Electrons always flow from anode to cathode. Okay? And guess what? This anode has to be positive because the battery makes it because it's connected to the positive. Okay? And then last step to get the salt bridge. How do things happen? Don't just put F comes down here because you see F and because there's F on both sides. Okay? So there is some leakage of F. But, by the way, AgF provides the fluoride ions here. Now, is fluorine good at oxidizing? Is F2 from your reference tables good at oxidizing? In your standard reduction potential tables, okay? In your standard reduction potential table, who is the top? Okay? Who is the top one? Fluorine. It is real good at what? In fact, if we had this in our environment, it wouldn't survive. It's too what? Of a reactant. Right. It's an oxidizing agent, the best. It reduces the best. Look at the positive volts, which means it's what? Terrible in going in the reverse. So this guy's not going to force and do anything. F negative, guess what? Spectating. Okay? It's terrible. Once it's in this form, for it to go back, you would need energy. Hey, we're not applying a battery to a battery. This is spontaneous, okay? And that is something you could use. So some of you guys use that into your overall. Use everything. Okay, so last little piece. If this is oxidizing, what's happening? Get that off. If it's oxidizing, that means a piece of solid what? Thallium is becoming thallium plus. The pluses are what? Building up. So we need a negative ion to come down. And I needed that to go there. What's happening over here? The silver plus is getting the electrons that are being pumped down. And so Ag plus is grabbing the electron and making Ag what? Zero, which is a solid. We're plating on the cathode. This is getting bigger. We're losing positives. Okay? So in this case, okay, the positive comes down to replace it. Now, if you had your battery opposite, I expected these to be opposite. I can't give you full credit if you made a mistake here. I want you to be consistent, no double jeopardy. So if you made this the cathode, you were banged for wrong if the K plus came down. Okay? You need to stay consistent with these problems for me. All right? All right, so now we're ready to rock and roll. So write the overall equation. Well, you should have a habit of doing the half reaction. Who oxidized? Cell B is the battery, right? So I kind of did this already. So write the half reactions. Okay, TL got oxidized. So what did it do? Became TL plus 1, plus an electron. Some of you guys had what? -2. My gosh, Oshkosh, no way. It's TL what? F. It's screaming to you what it becomes. All right? Now, what else happened? In the other cell, Ag plus an electron. It's nice and balanced for you. Became Ag0. Do not write the electrons in your overall because they're going to what? Cancel out. And if they don't cancel, it's not balanced. You balance the charge, you automatically balance the reaction. So these guys cancel. So the overall, of course, is TL0, or TL, plus silver plus 1, gives me AgO, and bingo was his name-o, and TL plus 1. Okay, yeah, maybe. Okay. Ooh, little tricky one here. What's the state of reduction for the TL plus and TL half cell. People got confused in this writing, but I didn't want to give away who was oxidizing and reducing. I was saying, in this half cell here, okay? Well, what did I say? Well, party people, I said that the voltmeter reading was what? Equal to E0 cell, electromotive force, is equal to positive 0.1 volt. Okay, now what do we know? We know that we take whatever's at the cathode, right? Whatever at the cathode, Christmas in July. Cathode is what? Red cat. It's reduction, correct? Who was my cathode? Okay, and what was happening here? Ag plus an electron. Now, okay, now, of course, I needed to go into my standard reduction potential tables. That wasn't given to me. So I got to find Ag plus. So here I go. Here I go again. All right, so where am I? So I go to my standard reduction potential tables. It's going to be high up because I know silver doesn't like to oxidize. It's at the bottom, and I can't get there because I'm too tall. All right, here we go. Maybe. So silver plus an electron is here, and if I move it over maybe, I can see that it's 0.80. Okay, so my cathode, do I flip that sign?
No.
No, it's as written because this is a standard reduction potential table, Christmas in July. Okay, now why? Why? Why is it all those listed? Why is it all that listed like that? Because it's a convention, right? What does a convention mean? Someone decided that's the way we're going to do it. So you deal with it. Sorry, these are all written as what? Gaining electrons. Okay? So guess what? The cathode is always the one that's as written. Okay? Reduction is always as written. Okay? I confuse people. Now, what do we do with that? Now, don't we add that to what happens at the anode? Okay, so let's solve for that. So what we have is, we have 0.8 plus Q. I like Q for instead of X. Q doesn't get used. Okay, it's kind of like an X if you think about it. All right, equals what? 1.1 volt. Okay, tough algebra. Solve for Q. Okay, what do you get? 1.14 minus 0.8. Okay, and so when you do that math, what do you get? You get 0.34. Now what does this tell us? This told us the anode's oxidation potential is 0.34. What did I ask for? The standard as written on the what? So we found that the oxidation potential had to be what? 0.34 in terms of how good it what? Think about it. If the silver pulls 0.8 really well, pretty good, and the what? Other guy pushes 0.34, you're going to have a total of 1.4. But in terms of the what? In terms of the what? The convention they set up, how would it be listed as a standard reduction temp? It'll be negative 0.34. If you forgot the negative, it is wrong. Okay, and I know that's a little nasty, but that's an AP problem. You have to pay attention to signs. Why? Signs tell me direction. Okay, moving on. Okay, backside. Going to go a little quicker here. Now for cell A, and of course this could be completely backwards if you messed it up. Okay, cell A, anode, oxidation. Because of this, I had to flip this the other way. Okay, and then of course this is reduction. So which one am I asking for first? I'm looking for reduction. Remember, I flipped this the other way because this is being made. So this is producing electrons. This is happening here. So my reduction is as written because that's the convention. So party people, here we go. So Christmas. Reduction, here we go. And I make a little thicker here. So reduction, I go Br, and people mess this up big time. Plus 2 electrons. Gives me what? 2 Br negative. Okay, and just for fun, I'm going to write the standard reduction potential. 1.065 volts was given to it. I'll write it right there. Okay, what was the oxidation? The oxidation was, was opposite. It's written because they're telling me that this is happening here. So the sign does what? Flips. So we write the opposite. Okay? People mention cosine of it. Okay, so here we go. I'm going to write it opposite. So I got Br2. I got 6 H2Os. And I get 2 BrO3 negative plus 12H plus.
He already bounced it out.
Christmas in July. Thank you.
He bounced it over.
I'm going to read it right. Okay, sorry. So let me just do it like this. It's 1/2. Thank you. As written from the other page, 1/2 Br2 plus 3 water. This was a little more advanced, but we can handle this. It's just balancing. It's stoichiometry. Balancing the electrons. Yes, you can. Okay, and what was the value here? Positive 1.52, right? Wrong, right? It's negative. It's going to be negative. Because we're flipping, okay? Flipping out here. Okay, now what's the overall? Party people. The electrons do not balance. So what's a common factor of 5 and 2? 10. So, new color because I just want to be color coordinated. All right, so I'm going to make this 10. How do I do that? Times everything by 5 times 1 is 5. 5 times 2 is 10. Now I want this to be 10. I times everything by 2. 2 times 1 is what? Okay. 2 times 6, 2, 12. Now we cancel stuff on both sides. Changing colors because I can. Okay, so I'm going to cancel out my electrons. Go bye-bye. Because 10 electrons, 10 electrons. 5 plus 1 is 6 Br2. Now I only have 6 waters over here. Okay, 10 Bs. Negatives, keep the same. 2 what? BrO3 ions. And then of course 12 protons, H pluses. E0 cell. I do not multiply this by 5 or this by 2. This is a what? A measure of spontaneity. It's a measure of how well they do individually, not how many electrons go by. So I just add them together. 1.065 volts plus a negative 1.52 volts. And notice we're going to get an overall negative value. Okay, negative 0.46 volts, which makes sense because it's what? A non-spontaneous cell. Okay, it needs energy to work. The battery gives it. Okay, number 9. Or as we say in Deutschland, Nummer 9. Okay, hören Sie zu. So now, 2 cells were connected 53 minutes with an amperage of 2.2 amps. After 53 minutes, the solution collected the molarity. So, oh my God, what do I do? What do you do last? The last thing I need to know is molarity is equal to the moles of stuff dissolved, hello, okay, over the liter of solution. Hello, they gave me the volume. So a quick little thing here, that liter, of course, is 0.237 liters. I need moles. I need how many BRs are produced. Remember, this is produced. Don't get lost in the sauce, party people. Okay? We are producing it. Can you see that? We're producing it where? At the anode. And it told me that oxidation had to occur, so that's everything's connected. All right, so moving forward. Forward if you don't like it. So now, here we go with our problem. Let's go find out. How do I know how much is made at the electrolytic cell? Well, the amperage is my link. Amperage gives me how much charge was needed to make it. Charge is due to electrons. This requires electrons. So, I need total time. So I'll take my 53 minutes. Go to seconds. Why do I go to seconds? Because my amperage is in seconds every 1 min. is 60 seconds. Now, once I have total seconds, now I use my amperage to get total charge. There's 2.2 amps. That means there's 2.2 coulombs of charge per every 1 second. Seconds go by, I've got total charge. Now I use Faraday's constant, fancy F, to convert total charge that was needed to make a certain amount of BrO3 over that time period to total number of electrons. And I want electrons because there's a relationship, stoichiometry, electrons to that. So, Faraday's constant, fancy F, pinkies up, I'm going to be fancy. Okay, and what do I know? It's 96,500 for those watching the same. Wait a minute, there's another Faraday's constant that's more precise, doesn't matter for me. And that's not volts, just seeing if you're paying attention out there. It's coulombs. And if I did put volts and confuse myself, guess what? Using my units, I know that I messed that up, and I put this on the bottom so I get rid of my coulombs to get what? 1 mole of electrons. And a mole tells me how much electrons. Hello! Stop! Not yet. We got moles of electrons. Okay? We have how many electrons it needs or is passed around in the current to make a certain amount of this in 53 minutes. But I want how many of these. So here's our stoichiometry. How many electrons? And notice I put electrons in the bottom. Why? They'll cancel. Equals how many BrO3s? And that's where a lot of people got this wrong. So guess what? I go back to my half reactions. For every 2, there's 10. Every 1, there's what? And if you don't like that, go back to the original half reactions. Every what? 1 of these. Remember, going this way, oxidation, anode. Every 5 of these, okay, there's 1. That's your stoichiometry. That's your relationship. Okay? And that's what I put there. And so many people messed up here. Electrons go bye-bye. And what do I have left? Moles of BrO3. And so I do my later of calc, bang it in there, and I get 0.0145. And this is mole of BrO3. That goes here. Solve for what? Make sure you convert that to liters because molarity is a ratio, how much stuff, moles. Okay, and you get something close to 0.061. And by the way, that's brackets. Or you can just say molarity or mole over liter. Okay, so many people, because they were robots, okay, I must convert to grams. Why? You need how many moles? Okay, last little piece. Please compare and contrast both cells. Explain their difference. Okay, you guys did a good job on that. Almost everyone got that right, except for Emma. Just kidding. No, everyone got that pretty much right. Hey, cell A, but I need you to say that cell A. Don't just talk about them generally. Hey, in my life, no. Cell A was what? Electrolytic, non-spontaneous, required energy. How do I know? This had negative volts. This one had positive volts. It was spontaneous. It was producing free energy that this was using. You cut these leads. Will this work? No, this drove it. So many ways to say that. Okay? So that is the crux. And those skills, okay, although it will be different, very similar to your test coming up next week.